So today we're going to be talking about power series and actually how to find something called the radius of convergence if it exists. And of course, these are very foreign terms for now, but we plan to sort of build up these ideas, and it'll take a few logical leaps to make, but once you see it once or twice, and once we do some more practice problems, you'll recognize that this stuff isn't actually too bad. But before we go into power series, I feel like we have to talk about something a little more important because we often see this in power series problems. What if I had something of this form, 2x plus 4? So how can I know, this is sort of an expression, how can I know when this expression is equal to 0? Well, if you're aware, you can actually set it directly equal to 0, and then you can solve for x. And the cool thing here is you will know for what inputs of x this equation is 0. So you can actually solve for x here. You can say this is -4, and then you can say x is equal to -4/2, and x is equal to -2. So this means that when x is -2, this essentially becomes 0. And this is a really cool thing, and I think a lot of people, they overlook it. But you can find out, let's say, I could make up anything. It could be random. I could say 3x minus 8. When is that, let's say, equal to 0? And then I could solve this. And then this basically says, look, when your x value is 8/3 and you plug it in here, you are going to get a value of 0. And this is true, right? Because we do this, we try to do this. We say, okay, really, is this the case? And if we try, you see that we get 8 minus 8, which is 0. So what I'm trying to tell you here is with algebra, you have the ability to set something equal to something else and solve for x, and you'll find out what x values make that true. And you can do this for other values too. Let's take 3x minus 8 and set that equal to 2. When is that equal to 2? And all you have to do, it's like magic, you can solve for x. So in this case, 2 plus 8 is 10, and then x is equal to 10/3. So if you plug in 10/3 into this equation, you're going to get a value of 2. That's insane. And so it's often looked over, but that's the idea here. And we use this a lot in power series problems. And we use it especially not when we're trying to find when something is equal to 0, but often we're trying to find when something is greater than 1 or less than 1. And what I want to say is, just as we set things equal to 0 and solved for x here, we can also do that like this. We can say, okay, when is this greater than 1? So what I'm asking here is, for what values of x can I put in this equation, and it will still result to a conclusion, to a value that is greater than 1? And you can solve this and you'll know. So we solve this here. 2x is greater than what? So we subtract 4 from both sides, right? We have 1 minus 4. We have 2x is greater than a -3. And then here, x will be greater than -3/2. So what this is telling us here is it's saying, look, you have this, you want to know when it's greater than 1. Well, guess what? Just solve for x. So when x, you can choose any x value you want, as long as it's greater than -3/2, your entire thing, this result here, after you input that value, it will be greater than 1. What if I wanted to find out when 2x plus 9 is less than 1, right? What do? I solve for x. I solve for x. So I can do 1 minus 9 here. I'll have 2x minus -8, and then x is less than -8/2. And so x is less than -4. And so it's basically saying that if you choose any value that is less than -4 and put it into this, then that value will be less than 1. And it may seem like this is sort of perhaps not relevant, but you'll see how it is relevant, and we'll talk more about that later. But before we get into power series, let me first say something like this. So what if you had something like this and you wanted to find when is this greater than 1? So what would you do? Oh, you want to find when it's greater than 1? Put that inequality there. and solve for x. In this case, we're solving for the absolute value of x. So this is saying when the absolute value of x is greater than 1 over 2, you can plug that into the original. You can choose any value as long as the absolute value of that value is greater than 1 over 2, then when you put it in here, it's going to be greater than 1. When you put it in here, that is. So this is a simple result here. But what if we had something a little more complicated? For instance, suppose we had something like this. We had 2x minus 1. We're going to put that in absolute value as well. And we're going to say that's less than 5. How do you solve something like this? Now, it's interesting because, you know, a lot of people, they think, okay, well, let me start isolating the x. But you can't do that in this case. Here, if this were 2x like this, you know, we can't isolate the x. It's sort of bounded by this absolute value. And so the convention is, and you can take this at face value, and you could, of course, research it on your own if you'd like, but the convention is that if you have x, let's say, less than 1, the idea here is that you say, you have x, or let me sort of generalize this, x is less than a. What you do is you do this, okay? You say, this is what you do. So this is sort of a formula, and I'm sure you could find this on your own if you searched hard enough. But the idea here is that whatever your absolute value of x is, you sandwich that in between negative a and a. And then you solve this inequality. So in this case, what would it be? In this case, you have 2x, and you're taking the absolute value here. Okay, you have 2x is greater than 1. So what do? Well, you take your a. So in this case, you take your x. This is our x. Before it was just x, but this is symbolically, you know, this entire thing is symbolically the x. So we take our 2x and we sandwich it. Let's actually make that less than here so that it matches our inequality. So we sandwich it between our a, which in this case is 1, right? Negative 1 and 1. And that's just dictated by, you know, we found our a, we sandwiched it between negative a and a. And then here we actually solve for x. So how do we do this if it's like a compound like this, right? Well, you can just divide everything by 2 here. Okay, you can divide everything by 2. So you're given this. Kind of like that. Okay, so this is basically saying when your x is greater than negative 1/2, but less than 1/2, then this will be true. Let's try doing this with this guy over here, right? Well, what do we know, right? We have our absolute value of x, right? Symbolically, this entire thing is the absolute value of x. And then you have that 5 here, right? Which is symbolically our a. And again, we're matching it to this, okay? So what do? Well, we sandwich it between, you know, the negative version and the positive version, and then we solve. So how can you solve? Well, let's start by adding 1 maybe to all the sides here. So what do we have here? We'll have negative 4, okay, and then we'll have 2x, and then we'll have 6 here. Now, how do we get that x alone? Well, let's divide by 2. Let's divide by 2, and all of this should come fairly natural. And then you would have 3, and then this is where it is true. So when your x value is greater than negative 2 but less than 3, then you know, this equality will hold, right? So you can choose any x value you would like and put it in here, and as long as it's greater than negative 2 and less than 3, your system works. Okay. And so that's the idea. That's a brief recap. If you want to figure out when something is less than something or equal to something, set it equal to that thing and solve for x, and out pops the value for which that would be true. So let's take a look at power series. And usually when we think about power series, we actually, they're sort of depicted in this form, where C of n is sort of a constant, or C sub n rather. And this x actually changes. So, for any input of x, you can sort of see that the series that you sort of develop is different for each and every value of x. So we start to think of a series as if though it were a function. If you're aware with functions, we have inputs, we put inputs in and we get out outputs. In this case, our input is x, just as if though we were dealing with a function, and out we get a series. So our output is sort of different in that regard, but the idea, the format for what a function is sort of the same, right? But usually you'll be presented with problems of this type, and it asks quite directly, what is the radius of convergence? And we'll talk more about that. But what the idea here is to solve this using the knowledge of testing series that we're sort of accustomed to. And usually these are solved with the ratio test or the root test. Now, I seem to think that most of them can be solved with the ratio test, although I'm sure there are a few glaring exceptions. But why not use some of the other tests? It's interesting, if you've ever asked yourself, why not use some of the other tests here? Why so stringently go towards the ratio test? Well, the answer is, suppose you were to use the comparison test, right? I mean, in the comparison test, we have an A of n, and the A of n is just the original, it's 2n minus 1. And then in the comparison test, we have a B of n. Perhaps you'd say that's, you'd strip off the constants and you'd probably say that's x to the n over 2n. But the issue here is that when you try to, have this equality or inequality here, it sort of, it goes against the purpose, because sure, it may be the case that this is true for certain values of x, but what if someone changed the value of x? Then what would you do? So it doesn't make too much sense to use the comparison tests with these guys, just because, you can say one is greater than the other, but what if you change the value of x? Perhaps then it will change, right? So probably not a good idea to use, the comparison test. This is sort of a very safe net. And so with that in mind, we'll apply the ratio test, and we'll learn as we go what the strategy is for solving these problems. But we'll apply the ratio test. And remember that the ratio test says, okay, well, get an A of n plus 1 out here. And once you have an A of n plus 1, which is, let's see what that would be. It would be x to the n plus 1 divided by 2. It's not going to be like this, okay? It's not going to be like that. You actually have to embed that plus 1 on the end. So you go around and you add a plus 1 to the ends wherever they occur. You can actually simplify this somewhat. You can say that this is 2n 2n plus 2, right? Minus 1, which invariably concludes this to being x to the n plus 1 over 2n plus 1, right? And that's sort of what we're left with. So you once you get these A of n's, you kind of you have to dance around them a little bit to simplify them, because you're going to be using them regardless. It's best to simplify them down. And then the A of n is just the original. It's just the original guy, right? I mean, we're not doing anything too difficult here. It's just the good old ratio test. And then what the ratio test says, it says, okay, well, take the limit as n approaches infinity of the absolute value. Okay, so we introduce the absolute value here of A of n plus 1 over A of n. So we'll do A of n plus 1, which is x to the n plus 1 divided by, what is the A of n in its simplified form? It's x to the n plus 1 over 2n plus 1. And then we're going to multiply by the reciprocal. Now I jump ahead here because, we're going to divide by this, and then we're going to have to flip the fraction regardless. So we'll just do that, without writing it, so that we don't get too verbose here. And then we ask ourselves, can we simplify, right? And we can. It's true, we really can, because we see that this is sort of a good target, right? Because they're both the same, so I feel like they'll simplify. And you can sort of isolate that by putting them one over the other. And you can see that x to the n is actually just x to the first, or x to the n times x to the first over x to the n, because of course, when you multiply these are the same base, different exponents, you have to add them, and then you'll get this. So we're just re-expressing it in a different form, and the goal there is to be able to cancel it out. And when you cancel it out, you're just left with x. So what do we have here? Well, let's see, right? So we will cancel these out and we'll be left with an x on the top. And you can see it's on the top. It's not on the bottom, right? Because then if it were on the bottom, you'd get 1 over x, right? But it's on the top because it's just x. And let's see what we have here. 2n minus 1. Can't do anything with that. Can't do anything with that on the top and the bottom. So here we are, right? I mean, just to recap, we're doing a power series problem here, and we wanted to apply the ratio test because comparing them is not consistent. And we do the ratio test, we do a of n plus 1, and we get a of n plus 1 by adding 1s to all the n's wherever we see them. We embed the n plus 1 here instead of sort of not embedding it. And then we simplify that down here, and we have our a of n, which is just our original. We put one over the other and we divide, and then we multiply by the reciprocal, noting that a over b over c over d is just a over b times d over c. And here we are. We've simplified it down by sort of doing some minor simplification on the xn plus 1 and the xn. And what do we do now? Well, it's interesting because you have the absolute value on everything here. But I'm going to say one thing, and I'm going to say that we can actually express this as this. This is where people look at me, they're like, what are you doing? And the answer is, I usually answer this question with a question. I ask them, well, you know, what if I had something like 1 over n plus 1? Or not the limit rather, but instead the series. So forgive me there. What would you do in this particular instance? So you probably want to solve this somehow, some way. But the interesting thing is that the absolute value bars don't actually do much here. The n actually starts from 1, right? And you know you go from n equals 1 to n equals 2 to n equals 3, and this whole thing tends to change. But it's always positive. It doesn't matter what it is, since n is always starting from a positive value and it's incrementing its way up. It doesn't matter what value of n you plug into this statement, it's always going to be positive. So what that does is it leaves the absolute value bars, it proves them as sort of being redundant, just because, you know, even if they're there, it doesn't affect anything. So why put them at all if it's always going to be positive? And we see much of the same thing here. This part, sort of this part here, it's always going to be positive. So, you know, why put that in absolute value? But the x is a tad bit different, because what if I throw a negative x value, right? So you want to sort of you know, refrain from taking the absolute value off the x, because that could very well, it's kind of like user input. The user can say anything, right? So the x can sort of be an issue. So this was the first logical leap. This was the first leap here that's sort of different than what we've been doing before. And the second leap, and this is leap number 2, and both of these leaps are often made in every problem. You know, we can pull this out, right? And this is where I sort of get held up at gunpoint by people. They're like, why are you doing that? You know, you can only pull out constants out of a limit, and they're right, they're not wrong. But the thing is that by the time the user, quote unquote, specifies what the x value will be, that would have been a constant. So it's kind of like we can pull this out here and just look at this. So what I'm really saying here is that, you know, for whatever x value we're talking about, it's not going to consistently change, right? It's going to be the same for throughout the entire problem. So while yes, it's a variable, it's also kind of a constant. So we pull that out and then we just evaluate this. And as we know, if the degree of the top is equal to the degree of the bottom, that's just the division of the coefficients. So here the coefficients are just 1. Well, the coefficients are 2 and 2 respectively, but that amounts to 1. And so here we are, this whole thing inside here is just 1, right? So it's just the absolute value of x times 1, which is just the absolute value of x. Now, let's take a step back here, okay? And this is where you have to start distancing yourself from your work a bit to sort of see, okay, well, what am I really doing? What you're really doing here is you're using the convergence test. I'm sorry, the ratio test. And what does the ratio test say? It says that when you're less than 1, if you take the limit and you're less than 1, then you converge. If you take the limit and you're greater than 1, then you diverge. In this case, we don't really know if it's greater than 1 or if it's less than 1. So what do? Well, we say that, okay, well, if the absolute value of x is less than 1, then you essentially converge, okay? And if the absolute value of x is greater than 1, then you essentially diverge. And that's sort of the idea. And we want to form an interval around this. And the interval is from -1 to 1. We sort of just take these endpoints here and then plot them like this. So if this were like, the absolute value is, let's say, less than 3, or the absolute value is greater than 3, then we'd say our interval, that satisfy this is -3 to 3. And so that's really the idea. Because it's kind of like this, right? It's kind of like if you put these two together, or actually that wouldn't be consistent, but that's essentially the main idea. And here we're more or less doing much of the same thing. And when you get down to this part where you have this interval, so to speak, what you do is you plug in the endpoints into the original you plug in the endpoints into the original series. Okay, so we're going to take this guy here and we're going to plug it into the original series. So we first plug in -1 and then we plug in 1, because we know that the interval is from -1 to 1, but we're unsure as to whether we include the -1. Do we not include the -1, and maybe we just include the 1, or do we not include any of them at all? And the idea is, if it converges when you plug it in, you include it. If it diverges when you plug it in, you don't include it, right? And so let's try putting in -1 to see where that gets us. We have n equals 1 to infinity. And then if we plug in -1, let's see what happens. So we plug in -1 here, -1 to the n over 2n minus 1. So in order to solve this, again, I mean, this is an alternating series test problem, right? So we're probably going to have to reference that here. And so this is the thing. These are why these questions are special, is because you got to use many tests to figure this stuff out. And so let me go ahead and grab the the formula, or really the cheat sheet for the alternating series test, so we can sort of see if this converges, we will include it, right? But if it diverges, we won't include it. So let's see what happens. So let's briefly remember what the alternating series test says. It says if you take the a of n plus 1 and the a of n, and this top statement is true, where the a of n plus 1 is less than the a of n, and the limit of a of n is 0, then we know it converges. So let's see if that's the case. We'll see if that's the case. So we take the a of n, which is just everything except that -1 to the n, and then we have a of n plus 1, which is just again, it's just what we have here, except we're adding that n plus 1 here, okay? And then we can actually simplify this down, right? 2n plus 2 minus 1, which eventually then becomes 2n plus 1. Which one is bigger? Is it this one or is it this one? And the answer is, well, you're subtracting the denominator from one of them, and you're adding to the denominator of one of them. The one that you add to actually makes the fraction smaller, because you're making the denominator bigger. You're dividing by bigger pieces. So it actually, it essentially makes that smaller. Here you're subtracting off from the denominator. You're dividing by smaller and smaller pieces. And so that generally makes this fraction blow up. Which means a of n plus 1 is less than a of n. This is one of the conditions is satisfied. Let's see if the limit of a of n is satisfied. So the limit of a of n, we just do this here. This is our a of n here. Is this equal to 0? And the answer is yes. We have that infinity in the denominator. We know that if we have a constant over infinity, that's 0. If we have infinity over a constant, that's infinity. Yeah, I mean, that sort of encapsulates both of those conditions. So what do we notice? It converges, which means we should include the -1. What about that 1? Let's try taking that same series and let's try putting a 1 in there. So if I do 1 to to the n, over 2n minus 1. Let me ask you this. If I put an n up there, does it really matter? I mean, if I had 1 to the 4, 1 to the 5th, 1 to the 6th, does it really matter what power it's to? It's just 1, right? So this doesn't even matter here. So we're looking at this series and we're asking ourselves, okay, we need to solve this. We need to figure out if it diverges or converges. What would we do? And the answer is you'd probably want to use one of the comparison tests, to be frankly honest. And the idea here is that, it's not geometric because we don't see to the power n's. It's not ratio because we don't really see factorials. It doesn't seem to be alternating because there is no -1 to the n of any variety. It's not just a p series. If we do the divergence test on this and we take the limit of this, it's 0. We want the divergence test not to be 0. And so naturally, one of the comparison tests will sort of work in this case. So with both of the comparison tests, we take a of n, which is just the original, and we take b of n, which is the original version, but you're stripping off the constants. And we can see naturally that since we're subtracting from the denominator of one of them, that one becomes the bigger of the two, because both of these are essentially the same fraction, right? Except from one of them, you're taking from the denominator. And if you're taking from the denominator, you're dividing by smaller and smaller pieces. Therefore, the fraction gets bigger and bigger. And so let's see which category we fall into with the comparison test. So we recognize that the a of n is essentially bigger than the b of n. So we're in this category. And it basically says for the a of n to converge, the b of n as a series must diverge. So really the question is, okay, well, we've satisfied the first condition where the a of n is bigger than the b of n, but does the b of n as a series diverge? Well, let's figure out. So we can take the 2 out like this. I'm sorry if that's actually really not coherent. We can take the 1/2 out, and we're left with 1 over 1 to the n. And we know that if we have 1 to the n, well, that's just an instance of the p series. And if the p is greater than 1, then we know it converges. If it's less than 1, it diverges. Also, if it's equal to 1, it also diverges. And so this is divergent, which means that so if both of these conditions are met, then we know that this diverges. So essentially, what we can say here is that, if we plug in -1, we seem to converge, but if we plug in just 1, we actually don't converge. So this would be the correct option here, where we have the closed bracket on the -1 and the open bracket on the 1. And this is often called the radius of convergence. From this range is the radius of convergence. So let's see what the second question holds here. So for this one, it seems like we have the summation of n equals 1 to infinity of x to the n divided by n factorial. Again, is this a power series? And the answer is yes, because we see that x in there. If you notice, any of the other series that we've seen do not have an x. Therefore, this is a power series. And if it is a power series, let's try to find that radius of convergence and stuff and so on and so forth. Again, let's resort to the ratio test for reasons stated in the previous problem. And also, it makes sense to use the ratio test here, right? I mean, whenever we have factorials, we often use the ratio test. So let's pull that guy out from the previous problem, and we will use, this is the alternating, this is the direct, and I believe we had the ratio test up here. Let's see, that isn't particularly helpful. I actually like to do this before the recording is in place, but at any rate, this is the ratio test. And what does it say? It says to take the a of n plus 1 over the a of n and take the limit of that, basically, the absolute value. So we're taking the limit of, well, what are we going to do? We're going to do the a of n plus 1. So what is the a of n? Well, the a of n is just what the normal thing is, right? I mean, it's just what we have here. That's the a of n. What is the a of n plus 1? Well, we're going to go around to the n, so we're going to add 1 to every n that we see. And this is actually a common mistake. It's very true. I see this very often where, they'll, in order to add 1 to the n, they'll just do this, right? And that's not the case. We want to embed those ones in there with those n's, right? So this is wrong. This would be right here. So now what we would do is we would take this guy, divide it by this guy, right? And we're taking the limit of that, the absolute value. So let's do x to the n plus 1. Okay, divided by, and again, I'm just sort of following the sheet here. And then we're multiplying by the reciprocal of the original of that a of n. So it in actuality, it's x to the n over n factorial, but we're going to do n factorial over x to the n, because what happens is we'd have to divide, right, by doing this. So might as well just do this, right? Let's see if we can simplify. That's always a good route when you're at this stage. What you notice is, again, I mean, you have this very common x to the n plus 1 over x to the n, which we know is just x to the n times x to the first over x to the n. And very nicely, these cancel out, and we're just left with 1x in the bottom. So you can see these two were a very clear target because they look the same. The one is kind of off, so maybe we can dance our way around it. And here we have it, right? So we have, it seems like we have x here, right, in the top. And again, I know it's in the top because, that's the way the math is worked out. And so really what we're left with is sort of this ugly looking thing, right? We have n plus 1 factorial in the bottom, and we have n factorial in the top. Let's try to, so if you remember, n factorial is equal to n minus 1, or you just place the n down first, and then it's equal to n minus 1, n minus 2, and then, so on and so forth. And if I had n plus 1 factorial, what would that be equal to, right? Well, I would put the n down. In this case, my n is n plus 1. And then I do n plus 1 minus 1, right? So n plus 1 minus 1. That's just n. And then I do n plus 1 minus 2. Well, that's just n minus 1. And then I do n plus 1 minus 3. That's just n minus 2. So you can see that, if I had one more factor here, n minus 3, everything after this point is the same thing as everything after this point. These two are the same. I'm not sure if this is apparent. These two are the same. So if all of this is n factorial, I can just say this is n plus 1 times n factorial, right? And then I can, I can either do it that way, or I could see that these will cancel out. Everything will cancel out. Even the n's will cancel out. And I'll just be left with an n plus 1 in the bottom if I were to divide both of these, right? So if I had this like that, I could say that, n factorial, okay. But I know n plus 1 factorial is the same thing as n plus 1 times n factorial. And then these n factorials would cancel out, right? Or again, I mean, you could go and cancel them out, and you'd see that the only thing left is, that 1 over n plus 1 there. And so it's all good in that regard, right? What did we say, right? What did we say? We said that we had this, and then the n factorial, and then in the bottom, we said that n plus 1 factorial is just actually n factorial times n plus 1. And these cancel out very nicely. And then the limit as n approaches infinity is just x over n plus 1. And this is the absolute value. And again, can I write this as this? And the answer is yes, right? Because look, I mean, if you have the, if you have this n is never, I mean, this inside here is never going to be negative. Your n is positive from the get-go, and you add 1 to it, right, on each increment. And so it'll never be positive. But that x, right, what if that x is negative, right? What if they throw me a negative value, right? Well, and then I want to put that absolute value there. I'm going to pull this out for the same reason I described in the previous problem. By the time we get to this point, that x is a constant. It doesn't matter what they throw at me. Whatever they throw at me is going to be a constant, right? And this is what we have. So what's the limit of this 1 over n plus 1? Well, we know that is going to be 0. When you have a constant over infinity, that's 0. So it's really just this times 0, right? And again, let's back up. We were doing the ratio test. The ratio test says if you're less than 1, okay, if you're less than 1, what tends to happen? You converge, right? So the interesting thing is that since I could give any value of x, I don't mind, and I'm always going to just multiply that by 0. So it's always going to be less than 1, which means for any input of x, it will always converge, always. And so it's kind of like this. It's from negative infinity to infinity. You can choose any value you want from negative infinity to infinity, both ends, both ways across the board, and it will always converge. So we want to know what the radius of convergence is. What is that? What is that range that of x values I can put where we'll converge? Well, it's negative infinity to infinity, right? Because I mean that's the I can use any value, and I will converge. So let's try to apply what we've been doing across the past 2 problems to this question. This is one of the harder ones, or at least it looks like it is. But really, the basic idea here is to do much of the same thing that we've been doing. And you may be tempted, right, to want to apply the alternating series test here. Remember, this is a power series, right? But you virtually have the freedom to choose whatever test you want, and you may want to do the alternating series test. And remember what the alternating series test says. It says if the a of n plus 1 is less than the a of n, and if the limit of as n approaches infinity of the a of n is equal to 0, then you converge, right? But again, it goes back to the same thing where, if you're less than, like, we're introducing these inequalities and stuff, right? And that's a problem. It's a problem because, okay, that inequality may hold. If a of n plus 1 may really be less than a of n, but what if we change around the x's? What if I throw you an x, and that changes the the inequality to this? What are you going to do then? And so, I mean, this is why doing that test just isn't going to work here, right? That x is a variable. And it will change. So we can't generalize this with comparisons. Let's go back to the ratio test and remember what the ratio test says. I'll just write it out here real quick. It says to take the limit as n approaches infinity of the absolute value of a of n plus 1 over a of n. And we want to see if that's greater than 0 or less than 0. Convergence if it's less, divergence if it's more. So let's go ahead here and sort of do this. We'll do n equals 1 to infinity. And since we're actually doing the ratio test, we actually don't have to include that negative to the end there. Because, actually we should be doing the limit. Because actually what tends to happen is when you do the absolute value, you ignore all the negative. You ignore all those odd powers that make this like -1, like kind of like, to this, right? This is still -1, right? So you're essentially, by putting that absolute value there, you're kicking out all the negative powers. And then you're just left with the positive powers, right? Like, not the positive powers, but the powers that make this positive, this one positive, like, like 8, right? But what you'll notice is that, like, it doesn't matter what the positive, I mean, the even power is, it's still always just 1. And if you multiply 1 by all of this, you still get 1. So when you take the absolute value, you throw out the -1 to the n or the -1 to the n minus 1. It doesn't matter what it is. You get that -1 out of there, and you're just dealing with what you're really dealing with once you're considering the everything but the -1 is the a of n plus 1, or the a of n rather, is just 4 to the n times x to the n over under root n. Okay. What's the a of n plus 1? Just a question here. It's 4 to the n plus 1 times x to the n plus 1, right? Divided by under root n plus 1. Okay, we're embedding that plus 1 wherever we see the n's, and this is going to be colossal, but it is what it is. We essentially take the a of n plus 1, right? And what do we want to do in this case? Well, we want to essentially put that, we're going to put 1 over the other, which means we simply we multiply by the reciprocal of the original of that a of n looking thing, right? And so this is kind of what we have, taking the absolute value of the first guy, right, the limit of, a of n plus 1 multiplied to the reciprocal of the original of this guy. So here it says 4 to the n times x to the n divided by under root x. Since we're going to do the reciprocal, divided by under root n, since we're going to do the reciprocal, we're actually going to do the opposite, right? Okay. And again, I mean, you look at this and you think, okay, well, let me try to simplify things. And it should occur to you that that these are two targets here, the x to the n plus 1 and the x to the n. I mean, infamous target, right? So n plus 1, x to the n plus 1 over x to the n. What do we have? So x to the n times x, we know that this sort of decomposes into x to the n times x, and this decomposes, well, this is just x. And this is what we have in the top, okay? So all things equal, we are left with the x in the top, and then we have that 4 to the n plus 1 there, and we have that under root n plus 1 here, and it's all multiplied by under root n divided by x to the n. Or actually, we canceled that out, didn't we? So there's really nothing there. It's just n. Because we canceled this out, right? Because, you're left with an x in the denominator. Because, if you divide them, they're kind of being divided here, right? They're multiplication. They're bonded by multiplication, but once you extend this bar, they're sort of being divided. So we can extract this piece out here and sort of assess it that way. You're just left with the x on the top. And you have that 4 to the n on the bottom, right? This guy, don't forget that guy. And again, you're doing much of the same thing. I mean, this is such a clear and easy target. You're looking at it, you're like, okay, well, 4 to the n plus 1 over 4 to the n, which is just 4 to the n times 4 over 4 to the n. This cancels, you're left with a 4 on top. How do I know it's on top? Because if it was on the bottom, I'd get something like 1 over 4. Okay, so you have the limit as n approaches infinity of what? Of the 4 on the top, x 4, or, well, let's call that 4x, right? Since, that's what we're used to. And you're left with the under root n divided by under root n plus 1 here, and it's all over, well, these are all in absolute value bars. And usually you'll see that when we get down to this level, we ask ourselves, what can we pull out to simplify our issue here, so that it's easy to take the limit. These n's, right? I mean, these will always be positive. We know this, right? And we can pull out the x. Remember what I said? I mean, that's a constant, right? It's a constant, but it could very well be negative. So we usually pull out the x, but this time let's take the 4 with us because we know that's a constant as well. So usually what we'll say here, the limit as n approaches infinity is 4x absolute value times all of this guy, which, I mean, do I really need an absolute value here if it's always going to be positive despite the value of n I put in here? No, right? And let me pull this out just so it's very clear to the audience that, what I've pulled out here. N plus 1. And what do we notice? The power of, the power is the same on the top and the same on the bottom. If you can't see the power here, actually, the idea here is that under root n is the same thing as n to the 1/2. So they both have the same power here in the bottom. So with that in mind, It's just 1. So it's actually just 4x times 1. Okay, the absolute value 4x. And let's zoom back out and really ask ourselves, what are we doing? We're doing the ratio test. So now it's not that simple, right? Now we want to ask ourselves, 4x, when is the absolute value of 4x less than 1? Because for those values of x, it will converge. Why am I suddenly doing this now? Well, we in the previous problem, we just had negative infinity to infinity. We didn't have to do anything. And in the other problem, it was just x here, right? And we knew it was less than 1 and greater than 1. And so in this problem here, we don't just have this or, this. In this case, we have this. We want to know when this is less than 1, right? Because that's when it's going to converge. And if we want to know that, well, just set it less than 1 and solve for x. Now, this goes back to what I was saying in the beginning of the video, where if you have the absolute value of x less than a, then what do you do to solve that, right? Well, the idea here is you sandwich the x sort of between two values of the a, that is, and then you solve for the x. In this case, our x is actually 4x, right? The absolute value. So we sandwich that guy between the positive version and the negative version, and we solve for the x. So we will do that now. How can we solve for the x? Let's divide everything by 4. Okay, so that means negative 1 over 4, x 1 over 4. And so this is the same thing as saying this. I don't know if you know this, but whenever you have let's say, let's say A, B, C, this is actually just saying that, right, your B is somewhere between A and C. A lot of people don't understand this notation, right? I mean, the idea here is that you're greater than A and you're less than C. That's just saying it's between, right? If you're between A and C, you have to be less than C, can't be ahead of it, then you wouldn't be between. And you also have to be greater than A, right? It's like 3 people, right? In order for me to be in front of, let's call this girl Julie. In order for me to be in front of Julie, my distance has to be greater than Julie's. But in order for me to be, behind, let's say Chris, I need to be less than Chris. My distance needs to be less than Chris. So this is effectively saying I'm between Julie and Chris, only if this condition is satisfied, right? So that's what this is saying. Like, you can choose any x value between negative 1/4 and 1 over 4, and this would be satisfied. You would converge, right? When we know it converges if this is satisfied, because we're looking at the ratio test, right? And the ratio test says that, do the a of n plus 1 over the a of n, and whatever you get, if that's less than 1, then you're fine, right? You converge. So we're finding that radius of convergence by using this absolute value business. But again, we don't know, and it comes back to the same thing. We don't know if this is, negative 1/4. We don't know if the negative 1/4 is included. We don't know if it's if it's not included, but the other guy is, right? Or maybe they're not, or maybe both of them are not included, right? So let's find out. Let's take the original series and let's actually put our endpoints here and see what happens. So this is our original series. Let me try to grab that here. Or actually, this is, yeah, so this is our original series here, up here. And this is taxing work. It really is. It's one of the harder problems, or the harder question types. Let me just start here, okay? And what we want to find out is, okay, well, let's try plugging negative 1/4, okay, negative 1/4. So if we do this, let's see what happens. Negative 1/4 for the x, this guy here. So this is negative 1 to the n times 4 to the n times, negative 1/4 to the n, right, over under root n. And you can actually multiply this, right? Like you have -1 to the n times -1 to the fourth to the n. That's just positive 1/4 to the n, right? So let's see here. That would be so 4 to the n times, it's just a positive, right? -1 times -1 over fourth is just positive 1 over 4. All to the n divided by under root n. And what you'll notice is like, okay, so, if you have like, a over b, right, over c, this is the same thing as a over b, right, times 1 over c, right? So the idea here is if you have a over b over c, you can just say a over b times 1 over c, right? So you can just, if that fraction's on top, you can just put it out front. You see here, it's on top, a over b is on top. We just put it out front, and everything else is the same. You can do the same idea here, n equals 1 to infinity. So this fraction is on the top, but we can just put it out front. We'll have this. Okay, and we can distribute this n here to everything. We'll have 1 to the n over 4 to the n, right? What we notice is this will cancel out with this. And again, 1 to the n, it doesn't even matter, right? Because it's 1 to the n, 1 to the fourth is 1, 1 to the sixth is 1, 1 to the billion is just 1. So we're left with 1 over under root n, and this is just a power series. And we know that by the power series, if you have 1 to the n to the p, 1 over n to the p, if the p is greater than 1, we diverge. We converge. If it's less than or equal to 1, we converge. Or sorry, that's the other way around. If it's greater than 1, we converge. If it's less than or equal to 1, we diverge. In this case, this is actually n to the 1/2, which means we diverge. So we're not going to include -1/4 here. Let's try the same process with 1/4. So we'll take the whole series in this case, and we will try to do much of the same thing. We'll try to plug in 1 this time. And if we plug in 1, let's see what happens, right? So so if I plug in 1 here, it will just be x to the first, it will just be 1 to the n, which is just 1. So I'm just left with all of this stuff pretty much. I'm just left with n equals 1 to infinity of -1 to the n times 4 to the n, right? Because if I do 1 to the n, if I plug in 1 in this thing, it's just 1, right, times all of this, which is just 1. So this is what I have. And let's see, missing something here. No. And this would be an alternating series problem if I'm not, let's see. Right, actually, you know what, we plug in 1/4. That's sort of our other boundary point. We plug in 1/4 instead of just, the, the 1 there, my bad. So we do -1 to the n times 4 to the n times 1/4 to the n, okay, under root n, right? And again, I mean, so let's see what we can do here. N equals 1 to infinity, -1 to the n times 4 to the n, and we'll bring that fraction out front, right? Just as I said before, that's just 1 to the n over 4 to the n, like that. These naturally cancel out, and we will be left with -1 to the n over under root n, which is an alternating series. Remember what the alternating series says. It says if a of n plus 1 is less than a of n, and the limit as n approaches infinity of a of n is equal to 0, then we converge. What we'll do here is we will say, okay, the a of n plus 1 is what? It's just all of this n plus 1. We don't include the -1 to the n, by the way. And then it's a of n, which is 1 over under root n, the same thing. We notice that this is actually bigger. The a of n is bigger because we're adding more here to the denominator, and that makes it smaller. And if we do that, we essentially satisfy this condition. Let's see if the limit as n approaches infinity of 1 over under n is equal to 0. It is equal to 0. So we converge, right? We converge. What does that tell us? So in the previous one, we found that, I believe we found that we diverged, right? So we didn't include it, right? But for this one, we have to include the 1 over 4. So this is the answer. So we have another one to look at here, and we are essentially going to apply the ratio test again, see what we can simplify. Let's try to do that. So with the ratio test, we just take the +1 version of the original, right? We take 2x minus 1 and n plus 1 divided by 5 to the n plus 1 times under root n plus 1, right? Multiplied by the reciprocal of the original, which is 5 to the n times under root n over 2x minus 1. Because in the original, you can see that it was like this, and I flipped it for the reciprocal version, right? We take the absolute value of that. Let's see if we have any cancellation properties. This one is a clear indication of being a cancellation property. So that's n plus 1 divided by 2x minus 1 to the n, which is 2x minus 1. And times 2x minus 1 to the first over 2x minus 1 to the n. This cancels. We're left with 2x minus 1 in the top. Let's just keep that in mind. We'll say that this is on the top here. Let's try to seclude another target, which is 5 to the n over 5 to the n plus 1, which is 5 to the n over 5 to the n times 5. This is equal to 1 over 5 in the bottom. And that actually seems like all we can do for simplification. So on the top, we have that 2x minus 1. On the bottom, seems like we have 5 times, let's see here. We have 5 in the bottom. And it seems like we have this here, right? We didn't do anything with these. Okay, so we'll multiply by under root n plus 1. This is absolute value. Let's try to take the constants out. I can't just take the x out of here, right? I mean, if I have some kind of constant like x and I multiply by 2 and I subtract it by 1, it's still a constant, right? So I'm going to pull this out and I'm going to pull this constant out. So really, I'm going to have this. Those are the only things that can be negative, right? These guys aren't really ever going to be negative and is always positive. And since this is a constant, it's going to be a constant eventually. Let me just pull it out, right? And by pulling it out, I actually have to do that. So I'll say this is this times the limit as approaches infinity, n over under n plus 1. Okay. This is 1. The power on the top and the bottom are the same, which means we're just left with this. What do we want to check when it's less than 1? We know that the absolute value of something like this, where this is a, is just minus a, less than x, less than a. And what we should do here is do the same thing here. So 2x minus 1 over 5 less than that a, which is 1. Sandwich it between the negative and the positive version. Let's multiply by 5 to get rid of this 5 here. We'll multiply by 5 here, multiply by 5 here, multiply by 5 here, these cancel out. We're left with -5, 2x minus 1, and then we're left with 5 here. Let's add 1 to everything, okay? These cancel out. We're left with -4, 2x, 6, and then let's divide by 2. We'll divide by 2 here, divide by 2 here, divide by 2 here. We're left with -2x, 3. And this is our interval from -2 to 3. So it's saying that when, so, you know, you converge when this is true and this is true when you're on this interval. But we don't know whether it's like this, whether it's like this, or whether it's like, you know, like this. Okay, which one of these is it? And the question is simple. We will take the original and we will plug in 3 and 2 into it and see what happens. This isn't too bad, I swear. So let's plug in -2. If I plug in -2 here, I'll have 2 times -2, which is -4 minus 1, which is -5 to the n. So I'll have this over 5 to the n times under root n. I can cancel these out, but I will have that negative, right? So it's kind of like this. Like if you're confused about this here, it's basically like this. I have -5 to the n, right, over -5 to the n. I can basically make this like -5 over -5, right, to the n, right? And that's just -1 to the n. So that means that this inside here is actually -1 to the n over under root n. Alternating series problem time, a of n plus 1 should be less than a of n, and the limit as n approaches infinity of a of n should equal to 0. So is the first condition met? Let's see. A of n plus 1 is the original without the -1 to the n, n plus 1. And then we have a of n here, which is 1 over under root n, which is the original without the -1. This is clearly bigger because we are sort of adding numbers to the denominator here, so the denominator gets smaller. And the limit as n approaches infinity of a of n is also equal to 0 because a constant over infinity is equal to 0. Therefore, we converge and we should include the -2. And so we'll include it here. So we'll say -2. For the 3, let's try to plug 3 into this thing and see what we get. Do we converge? Do we diverge? That's the $1,000,000 question. And if you plug in 3 into here, you'll have 2 times 3, which is 6 minus 1, which is 5. So you'll have 5 to the n over 5 to the n times under root n. And this is going to just be a p-series, which is divergent. And if it's divergent, then you don't include it. And so it's like that. That's your answer. So again, I mean, like all these problems are pretty much the same. We apply the power, the ratio test. And once we pull out the things that don't need to be in the absolute value. Once we pull those things out, we solve for when it's less than 1 because we're doing the ratio test. We want to know when it converges, and it converges when it's less than 1. And then we set the inequality, right? And once we have the inequality, we plug the n bounds into both and then see if we diverge or converge by using some of the other tests. Let's move on to absolute convergence and conditional convergence. Let's talk for a bit about this idea of absolute and conditional convergence. So suppose I had some kind of a series. I'm going to call that series a of n, and suppose it converges. Okay, fine. But then suppose I took the absolute value of a of n, and that also converges. So the original of a of n, right? The original converges, fine. And if I take the absolute value of that series and see if it converges or diverges, that also converges. Then I'm going to say, let me see if I can actually, put like a shape here or something. No shapes, no shapes. Then I'm going to, I don't know what that is. What is that? Then I'm going to say, so if the normal converges and the absolute value version converges, then I'm going to say that it is something called, it's absolutely convergent. I mean, there is no doubt that it is absolutely convergent without a doubt, right? I mean, there's no doubt it's convergent. The absolute value version converges, the regular version converges, you are absolutely convergent. But what about if I had the absolute value, A of n, and we know that hypothetically A of n converges, right? You use some type of test to find out if it converges or diverges. And then you took the absolute value of that, and that diverges. Well, then you are conditionally convergent. And the idea here is that the condition is that you're convergent, sure, but if you take the absolute value of it, then you're divergent. Okay, that's the condition. That's why they say it's conditionally convergent, because you're convergent, but not if you take the absolute value of it. With the condition of, if you take the absolute value, you essentially diverge. So some problems, what they say is they're saying like, test if it converges or diverges. But other problems will actually ask you, is it divergent? Is it absolutely convergent, or is it conditionally convergent? There's no such thing as conditionally divergent, so don't even worry about that. You're either divergent or you're not. If you're divergent, then the absolute value version won't be convergent. Okay, so if you're divergent, you're just divergent. End of story, right? I mean, pack your bags and just dip out. But with convergence, you can see if you're absolutely convergent or conditionally convergent by taking the absolute value, okay, and then seeing what happens, and then pitting it up against this whole idea. So let's look at this series, and instead of just asking if it converges or diverges, we're actually going to change up our question here. We're going to say, is this absolutely convergent? Is it conditionally convergent? Or is it divergent? These are your three options. So first, let's just test the normal series. And let's see if it's convergent, right? If it's divergent, then we don't even have to see if it's conditionally or absolutely convergent. So if you were to do this test, you would probably want to use the alternating series test, right? The alternating series test is essentially used when you have a -1 to the n usually. And what we know is that the test says if a of n plus 1 is less than a of n, and the limit as n approaches infinity of a of n is equal to 0, then you basically converge. So let's see if that's the case. So what is the a of n? The a of n is everything but the it's everything but the -1, and the a of n plus 1 is actually just going to be let's see, so we would add a 1 to the n, right? So this is obviously going to be bigger in this case. Since we're adding more to the denominator here, this becomes smaller. And so that satisfies the first condition. The second condition is basically that the limit as n approaches infinity of the a of n, not the a of n plus 1, but the a of n, is equal to 0, which it is. So the second condition has also been met. Therefore, we can say that this is convergent. So let's make a note there that the a of n is convergent. Okay, but what happens if we take the absolute value of the a of n? Remember, when we take the absolute value, we drop the -1 to the n plus 1, which means we're just left with this. And this is no longer an alternating series test. When you test this series, it's no longer an alternating series test. Now it's just a p-series, remember that with a p-series, 1 to the n, 1 over n to the p, if the p-value is less than 1 or equal to 1, you essentially diverge. If the p-value is greater than 1, you essentially converge. Here, the n can be written as n to the 1/3, and basically you that's less than 1, so you diverge by the p-series. So if you take the absolute value, it turns out, of the a of n, you actually converge. So it seems like, that's not gonna, it's not absolutely convergent because while the regular one is convergent, if you take the absolute value of it, it'll actually diverge. So this one you would say is divergent. Sorry, conditionally convergent. And the condition is you're convergent if you're normal, but if you take the absolute value version, you actually diverge. So you're conditionally convergent. And the condition is don't take the absolute value or else you'll diverge. So let's ask ourselves the same question by looking at n equals 1 to infinity of, let's say, -1 to the n plus 1 over n times under root n to the third. Or actually, yeah, this works. So is it conditionally convergent? Is it absolutely convergent? Or is it divergent? Which one of these three, sort of meets the criteria? So let's just try to figure out if it converges or diverges, normally by using all the tests that we have. And what we notice here is that this is an alternating series test problem more than likely. But let's simplify a bit, right? Before we get into actually solving the series, let's sort of simplify here. N plus 1 divided by, so when you're doing n times, under root 3n, n, that's the same thing as n to the 1/3, right? And look, so it doesn't matter, right? If you have a 4 here, that's just n to the 1/4. If you have a 6 here, that's just n to the 1/6. So this is what you have. And when there's a 1 here, obviously. So when you have the same base but different powers, you can do that. You can add them. This is 1 plus 1 over 3, right? So what's 1 plus 1 over 3? That's the same thing as asking 1 plus 3 over 3, which is 4 over 3. That's just n 4 over 3. So that's just n to the 4 over 3. So now we can sort of, it's easier to work with, right? Let's use the alternating series test. The alternating series test says if a of n plus 1 is less than a of n, and the limit as n approaches infinity of a of n is equal to 0, then we converge. So a of n plus 1 is just this thing. I add 1 to all the n's except the -1 to the n plus 1. So that's just n plus 1 to the 4 over 3. And then the a of n is just the regular guy, right? Or just the regular a of n, right? And then we can clearly see that this is bigger. So we meet one of the criteria. And the other criteria is that the limit as n approaches infinity of a of n must be 0. So if we take the limit of this, it's 0, right? And therefore we converge. So basically the normal version of a of n is just convergent, right? Let's find out if we take the absolute value of this, do we converge or do we diverge? If we converge, we'll say that the absolute value version converges and the regular version converges, so it's absolutely convergent. But if we take the absolute value version of this and it diverges, then we'll say that it's conditionally convergent, and the condition is that you don't take the absolute value. So let's go ahead and do that. So we'll take the absolute value version of this, which is just the same thing without the -1 to the n plus 1, which is n times cube root of n. Okay, which we already said was the series of 1 over n to the 4 over 3, right? Did we say it was 4 over 3? Yeah. And we can clearly see this is a p-series problem, 1 over n to the p, where p is greater than 1, we converge, and if its p is less than 1, we diverge. And so in this case, we will basically say that since this is 4/3, 4/3 is greater than 1, we basically diverge or converge here by the p series. So if we do the regular one, it seems like we converge. And if we do the absolute value version, it also seems like we converge. Therefore, we're absolutely convergent.